So next I'm pleased to welcome George Petrie. He's got 25 years of experience as a professor of naval architecture at Webb and 35 years of experience as a consultant in the offshore engineering space, and he's the Seasteading Institute's Director of Engineering.
Oh, okay. Which way?
Right for forward.
He was taking away my laptop. Okay. Thank you for not going any farther back in my my resume. I am the Director of Engineering. The theme for my talk this morning is basically where we have been, where we are today, and where we're going to be going in the future. And actually, I am myself going to take us just a wee bit farther back in my biography. As I was looking back at the history of the Seasteading Institute, I became a little bit carried away and was thinking how almost to the beginning of my professional career saw the foreshadowings of my involvement in this type of a project. I've always been kind of attracted to unconventional thinking. I graduated from Webb Institute with a degree of naval architecture 4 decades ago, and virtually all of my classmates went off into designing commercial ships and you know, military ships, things that went in the water and went from place to place like proper ships do. And I found myself in a rather odd project designing large oceanographic data collection buoys. And it's like every time I turn around, I'd have to explain to somebody what it was that I was working on. And that was kind of a foreshadowing of here I am 4 decades later working on large platforms that will likely be anchored in the deep ocean, just like these buoys that I started working on those many years ago. Those were relatively small, unmanned. These are going to be relatively large and populated. But the foreshadowing seemed to be there. And from that experience, my next activity professionally was working for, in the late 70s, early 80s, company doing consulting in the offshore industry, basically looking at, and this was in the dawn of the activity in the North Sea, and a lot of the companies that had been working successfully in the Gulf of Mexico found themselves functionally challenged in different environments. So I kind of evolved professionally to be looking at how the sort of form follows function, how does the platform have to adapt to the environment. And that plays into some of the things we'll be talking about. I then segued into teaching at Webb Institute, but continued consulting in the offshore business. In connection with my teaching activity, I happened to take a 1-year sabbatical, half a year sabbatical, was over in China for 8 months, perchanced a couple of years ago to sit in on at an engineering conference, sit in on a presentation on something called Floating Cities at Sea. And I was looking at the other papers and I said, boy, that sounds like a winner. And halfway through the presentation, this was the Clubstead, the Clubstead project. And halfway through, I'm like, pick me, you know, how can I get in on that? That sounds really cool. And at the end of the presentation, we exchanged cards, and the folks doing the presentation basically said, well, you know, they just hired us to do this. We're contractors. As soon as the check clears, we're done. But talk to James Hogan was James Hogan was Randy Hankin back in the day. And 2-3 weeks later, a couple of emails, phone calls, and I found myself as the Director of Engineering. And it's, you know, I got attracted to it because of really the engineering challenges, the possibilities of these communities at sea. First time I went to the website and saw all the libertarian spin, it's like, whoa, holy cow. That's lagniappe, as they would say in New Orleans. It was just way too good. And I've now hung up the chalk. I'm no longer teaching. I'm consulting full-time. Seasteading is one of my primary clients, but I do some other things. One of which involves I'm consulting with a project in a shipyard in Galveston, and every day as I drive to my office in the shipyard, I drive past a large semi-submersible oil platform that has been sitting forlornly for way too long, just waiting for someone to come along and breathe new life into it as perhaps the foundation for a future but not too distant future seastead project. So, you know, these threads just kind of run through my life. I was also kind of taken by the quote from Bill Reedy's presentation from Dr. Knox,
Yes.
who basically said, you know, in the marine industry, you know, we really don't do a lot of innovating ourselves. We pick and choose, and we adapt, and we adopt, and we make it all work together. And that's basically my vision of my role as the director of engineering is we frankly don't have the resources to do a lot of the development that we might like to do, but we have the wherewithal to keep tabs on what's happening in the rest of the world and pick and choose the best technologies, the best solutions to deliver, and our objective really is to deliver safe, comfortable, and affordable accommodation at sea to facilitate this grand vision. So, just briefly to recap past activities, I'd mentioned the Clubstead report. That was basically these past activities over 2008 to 2011 timeframe are basically kind of big picture questions. The Clubstead was just to sit back and say, is this even feasible? Are we smoking dope? Well, that's not a bad thing. Is this even feasible? Or are we just totally off the wall and even trying to do this? And the takeaway was, yeah, it's not out of the woods. And then the next two studies, we're looking at things that exist now in terms of technology for accommodating people offshore, and in terms of where to actually put seasteads. The first question was, what should we even be looking at to make the decision of where to put them? And then on the engineering side, what questions should we be asking ourselves to decide what platform is good, what engineering choices are good? And finally, the most recent study that we did that I have on the past activities list is a study on the floating breakwaters, and I'll talk just a little bit about each of these. The Clubstead preliminary feasibility study, basically the takeaway, aside from intriguing me enough that I'm standing here today, the main takeaway from that was, you know, what might such a seastead look like? Kind of how much would it cost? Economically, is it feasible? Is the concept viable? And the full details of that in excruciating detail are on our website in that report done by MINT consulting organization. The next of the past activities I want to mention is a study by an intern, Miguel Ramos Pardo. He has created a report just looking at what he calls coastels, nearshore floating accommodations. Over on the left-hand side is an actual industrial floating accommodation platform on a pretty much flat-bottom barge with a kind of an ugly superstructure. and putting the artistic creativity to that, we can transform that into something that looks a little bit more stylish, not unlike some of the floating casinos along the Gulf Coast and other places. But again, I wouldn't go more than 6 feet offshore in one of those, but it's a floating accommodation platform. Oh, that's bad. The background covered the slide. Sorry. Okay. Well, you can just kind of remember what those look like. Okay. So for more offshore capable situation, we've got floatels, which are floating hotels for open ocean areas. On the far right is a ship-shaped accommodation platform. Think of it as kind of an industrial strength cruise ship with a lot of hotel-like spaces inside and some heavy cranes and a helideck, and it's really strong for offshore industrial pursuit. Nice place to work, but I wouldn't want to live my life on that. For even more hostile waters, we would have a semi-submersible type of accommodation platform. The same deal, big floating hotel, industrial strength, heavy duty, big cranes. That's overkill as far as what we need for outfitting, but as far as the platform concept is concerned, if you're going to be in rough waters, that's where you need to be. And this kind of plays into, let me try and go back here. I mentioned my first job as a consultant looking at basically flat-bottom barges that were very successful in offshore construction in the Gulf of Mexico, relatively benign. Those same vessels went over to the North Sea, they got hammered, which is why platforms such as this were developed to cope with the much harsher environment. Now, the downside is those are much more expensive, and it becomes a matter of, I need to know how challenging is the environment before I can decide how much money I can justify spending for this solution as compared to that solution. Okay. The next study that I want to talk about just a little bit is the location study criteria. I'll talk more about the actual location study itself, but that was preceded 2 years ago by an internal study asking ourselves, if we're going to decide where on earth to put a seastead, what questions should we even be asking ourselves to make the right decision? And environmental, legal, political, and economic. Similarly, as a kind of a background big picture study, another intern, Elko Hagedorn, and I mention these partly to give them credit and partly to kind of highlight the fact that when people talk to me, and I'm the director of engineering, and they ask me, well, you know, how many people do you have on your staff? It's like, yeah. But we managed to engage a lot of people, and this plays into the thread that Petrie mentioned is in terms of partnerships and networking and so forth. And it's one of the cool things about this organization. So as far as engineering criteria, that's what Mr. Hagedorn put forward in his report. This, again, as each of these reports are on our website, unspoken, but every bit as important, as I mentioned at the beginning, safe and affordable. That's paramount. And finally, the last of the kind of completed works is a work done by two Seastead interns just a year ago, evaluating existing floating breakwater and wave power generators. This is most of the engineering work that is going to occur is going to be in the realm of adopting and adapting and so forth. I don't think that there's anybody out there who is is actively developing large floating breakwaters to deploy in the middle of the ocean. That's something we're going to have to really take the lead and figure out how to make that research happen. And one of the partnerships Petrie mentioned previously is the FDN Flowtech joint activity. We're hoping to get some high-powered sponsors to fund that activity. But as a background, this was kind of a survey of state-of-the-art. Here's what exists currently in floating breakwater and wave power technology. The idea is rather than having a breakwater that just stops the waves, you make it into something that transforms the potentially destructive wave energy into something useful called electrical energy, electrical power. All right. Now, the next portion of the presentation, and how am I doing on that time? Okay. Where we are, we have recently completed or are still actively engaged in this set of projects. Actually, doing the location study was completed just within the past year. The parametric engineering analysis is a two-part project that I pretty much did on my own with some support from a number of folks, but that's pretty much my deal. Sustainable energy options, we will have presentations later in the day by Melissa Roth and Guillaume Ardois addressing specifically sustainable energy options, and we've got a couple of other more specifically focused presentations relating to energy. And the last of those projects I'm going to mention are the what I call creative deck house designs. Those have been done pretty much by volunteers and interns and student projects, and they're just kind of interesting. So let's see if, okay. Okay, the seasteading location study was basically to look at all of the environmental parameters, wind, wave, current, depth, air temperature, economic factors, legal and political factors, and to number one, and not an insignificant challenge, was finding global data sets for all of those disparate things. And that was a real big job to find those data sets so that we could effectively scan and filter the entire Earth to find the information we needed to make a good decision or to gain insight on where we should be placing these. Now, as an engineer, you know, we like to make graphs and charts and equations and so forth, and you know, come up with some kind of a mathematical measure of merit that says, you know, this is good and this is not so good. Well, I don't know how you stir wind speed in knots and proximity to urban areas in miles with legal status that even defies mathematical quantification. You know, how do you stir all those into a pot and come up with something? So after acquiring or locating the databases, we came up with a series of transformation functions that would essentially score all of these disparate criteria and put everything onto a common scale, rather arbitrarily defined, but a 0 to 1 to 100 scale. 100 is really good, and 1 is really not desirable. And on that basis, we could normalize, transform all of these things onto a common numerical basis. And so we've we've now got all of these quantities on a 1 to 100 scale, and it's like, okay, how do I weigh wind and current versus proximity to urban areas versus legal status versus dangerous regions, pirate attacks? How do I equate all of those? And so the next challenge was to develop a scheme for weighting each of those variables in relative importance to certain scenarios. And there is no one-size-fits-all solution. It's somewhat akin to saying, well, what's the best place in the country to locate a factory? Well, what kind of factory? What are you going to build? What resources do you need? How important is transportation? How important is water access versus highway access versus access to bright, creative people like you have here in Silicon Valley, as opposed to people that are willing to work for, you know, $250 an hour plus tips. You know, it depends on your business where the best place is to locate. And so the scenario weighting functions are kind of the application-specific weighting factors. And after we had conquered all of those, how are we going to do this things, we were able to then, using the GIS type hocus-pocus programming, create some what we call scenario heat maps, which allow us finally to visualize the results. Just to kind of take you back a little bit, the data transformation, we have, in this instance, water depth from minus 10,000 meters to plus 8,000. Obviously, those are the mountains. All of the negative values are water. You can see the very deep ocean areas, the ocean subsurface mountain ridges. So we just transform that from depth in meters to desirability on a scale of 0 to 100. Now, if you're talking about a moored platform that has to have anchors touching the bottom, it's obviously nice to be in shallow water. Mooring in 2,000 meters of water is very hard, very costly. If you're talking about a platform that's going to be dynamically positioned, that is held in place by its own propellers, kind of idling in position, if you will, water depth is like, I could care less, I don't care. 10 meters, 1,000 meters, all the same. But things like wind or current become much more important, because if you're dynamically positioned, every knot of current or every knot of wind is more fuel you have to burn to be where you are. So the importance of certain environmental parameters is heavily a function of, is it a moored platform? Is it a dynamically positioned platform? Now, as an intermediate step, we created aggregation layers, which take a kind of a sub-weighting of all of the environmental things to tell us, from an environmental standpoint, we want to be in the green, we want to avoid the red. From an economic standpoint, again, we want to be in the green and avoid the red. We see instantly that a lot of the places environmentally that look good from an economic standpoint, not so good, depending on the assumptions. And legal considerations, which includes dangerous waters. We see the flaming red areas to be avoided on that basis. So if we weight all of those different things, and the aggregation layers I just showed you are also dependent on the scenario. So we don't just have a single set of aggregation layers. Those two depend on the scenario. But the final takeaway for a shipstead, which is basically an enterprise that is maybe based on something akin to a converted cruise ship, would be dependent on proximity to land for labor, for markets, for a lot of economic activity. It is desirable to be close to the shore. And so you see the dark green areas, the most desirable locations are near shore locations. And by contrast, what we call Metropolisstead, which is the grand vision on the hill, the city of 50 to 100,000 people, which has its own economy and its own infrastructure and is more or less economically independent of proximity to land. There's families, they have kids, schools, they're self-contained. It's almost just the opposite. The places that are deep green here are not so green over there. The Metropolisstead doesn't necessarily want to be near land. It wants to be off on its own, doing its own thing. Depending on the assumptions for any particular model, we'll get a different series of heat maps. The takeaway from the location study is, here's the tools, here's the data set, here's the mathematics for the transformations. In a very simplistic manner, plug in your weighting factors to suit your business model, and bam, you get a visualization of the most desirable places to be. Okay, now we get to my stuff, the parametric engineering analysis. And I apologize, I should have jazzed this up with a couple of pictures of semi-submersibles and ships and barges. But basically, I show this rather dismal slide to kind of underscore the fact that unlike a lot of the visualizations that you see of what seasteads are, those pretty cartoonish pictures, we've actually done the real engineering analysis. We've sat down, we've crunched the numbers, and for semi-submersibles, which are column stabilized platforms or ship shapes or barge shapes of different lengths and different proportions, here's what you get for capacities and cost per square foot or cost per residential unit based on a certain size. And the takeaway is that in the second to last column, we see numbers approaching the same, more or less $300 a square foot that Clubstead came up with. We weren't quite as optimistic in our assessment as the Clubstead folks are kind of acknowledged to have been. But we can see that costs in the 300 per square foot neighborhood are not out of the realm of reason. Petrie mentioned that I am currently doing a next level of detail to get a better handle on the costs. I don't have a slide on that, but that refinement of this activity is in progress. Can't have an engineering presentation without some graphs. This is the relationship between, for ship-shaped platforms, barge-shaped platforms, if you make a really small one, you have really high cost per square foot. As you make it bigger, economies of scale. And we were interested more in identifying where the breakpoints are. For barges, for ships, not such a well-defined breakpoint. And for the semi-submersibles, we did different density of populating the deck house with accommodation spaces. Again, this is, we crunch the numbers like engineers do, and the report is on the USB card. Part one of the report produced the preceding tables and graphs. The second part was looking at the platform performance at sea, and we're using criteria for comfort and endurance in terms of side-to-side rolling motion, vertical acceleration, which is the elevator is starting very slowly, or the elevator is starting with a jerk, and that's very uncomfortable, or lateral acceleration, which is the tendency to knock the wine glass off the table, which is really annoying when that happens. So these are not limits that we made up. These are actually published, widely acknowledged limits for comfort and endurance for those degrees of freedom. We, again, crunched the numbers to figure out how much barges versus ships compared to semi-submersibles, how they will roll and move up and down and move side to side. And then you put that mind-numbing, I mean, literally millions and millions of tables of numbers, and you stir that into the probability of different wave severity occurring. This graph is showing the North Atlantic compared to somewhere off the coast of Hawaii. Generally speaking, the higher and to the left is a more benign environment. The lower and to the right is a more severe environment. If we show the intermediate graph of how each platform responds to different waves, we can create summaries for each of the 12 different ship configurations based on each of the comfort and endurance criteria in Hawaii compared to the North Atlantic. In a very benign environment, the small ships are kind of okay, but in the North Atlantic, not so much. The barges, pretty much not going to work anywhere. The semi-submersibles pretty much will work anywhere. And again, this is largely confirming what people intuitively understand, but to get from an intuitive understanding to really making decisions, dollar and cents, if my business model says that I need to locate in an area where the waves really are severe, that might not be my choice, but if the business model says, no, I need to be there because maybe I'm doing deep ocean mining, and that's where the magnesium nuggets are to be found, and that's the core business of my seastead, I need to figure out a way to be there in safety and comfort. And it's worth spending the money to build a platform that can withstand that environment. But if I don't need to be somewhere, if I can get by in my business model in a more benign area, then I don't need to spend the money for the big semi-submersible. Maybe the ship, maybe the barge is going to be just fine. And so we've got the methodologies to crunch the numbers to make those informed judgments. Now, the next series of works in progress are sustainable energy initiatives using conventional diesel generators as baseline, looking at solar, wind, wave, and ocean thermal. And I'm not going to say anything more because we got some very detailed presentations to follow on those subjects. And, oh, I did have it. Okay. I mentioned my current consulting gig. I drive by this wonderful old oil rig on my way to Galveston every day. This is a 40-year-old oil platform that has served a valiant career drilling for oil in the oceans of the world. It was retired several years ago. Some entrepreneur came along and decided he was going to retrofit it to some other purpose. Like so many good intended startups, ran out of money. So here it sits kind of half finished. All that scaffolding is just temporary scaffolding for access. The platform itself is just waiting for someone to come along and finish the job and make it into a seastead. Just to kind of inspire the imagination about what that might look like, one of our volunteers created some interesting renderings about how you might make that old rusting hulk into something really pretty jazzy looking. Okay. Now the concluding set of slides, I'm just going to talk briefly about where we're going in the future. Certainly sustainable energy initiatives is high on our list. Among other things, there are two real imperatives. One is the fact that since I was a wee tot, which is a long ways a while ago, you know, it's a recurring theme, energy independence. You don't want to be depending on others for your essential sources of energy. And just, you know, if you're going to be politically independent and economically independent and so forth, why shouldn't you be energy independent as well? And from the standpoint of just public perception, we're trying to do something bold and daring, and why go out and, you know, bring in the fuel barge and fire up a noisy diesel generator? No, do something cool. Do something befitting how cool this whole technology is. Floating breakwater, we've talked already. One of the other major issues relates to modularity and scalability. If you want residents, if you want communities to grow, they need to be inherently scalable. And if you want residents to be able to vote with their feet, they need to be modular so you can pick your residents up and go somewhere else. Materials and fabrication. Okay. I'm running low on time here. So these are the sustainable energy initiatives, the floating breakwater. We've mentioned the joint proposal with FDN and Flowtech. I wanted to get to the modularity and scalability. We've got modularity on two levels that we're dealing with. One is the Intra platform modularity, which, if you recall back to the rusting semi-submersible photo, I envision that as basically an at-sea trailer park, a flat deck with standardized plumbing and electrical hookups, and people could conceivably build their own individual accommodation to standardized dimensions and interfaces, and at some point hire a crane and just place that on the deck, like setting up a mobile home in a trailer park. And if they didn't like the environment, if they wanted to move to the trailer park or the seastead 10 miles down the pike, they just pick up and move along. So that's the Intra platform. Now there's also inter-platform modularity and scalability. If you want to have seasteads grow from one platform to many platforms, how do people get from one to the other? Do you physically link them? Do you link them with gangways? Do you link them with water shuttles? How do you do that? We're also looking at materials to achieve long life and low maintenance. Welded steel is kind of the dumb default. Hybrid construction to keep the steel deck, the steel structure, but the deck house can be lightweight material. reinforced concrete, and we are, Jim, also looking at the use of composite materials, because that is part of lightweight, low maintenance, long-term viability. So we're going to be looking at all of those options as we go forward. And finally, modular construction, how do you actually achieve economies of scale by building multiple units? Station keeping, mooring versus dynamic positioning. Lazy station keeping is kind of dynamic positioning. Just kind of drift with the current. And communications. I left this slide till last because I don't know anything about it. You know, help, help. And finally, where we're going, possible scenarios for the first Shipstead. Petrie kind of gave a thumbnail of that earlier. And so, if I have any time remaining, questions. But here is that same oil rig back in the day when it was actually a functioning oil rig. This is Aaron's visualization of it, and long-term, the shining city on the hill. Yes, sir. Question?
Patrick doesn't want me to ask. One question. One of the questions that came from the last Seasteading Conference was what the portion of labor cost was in platform building. I think we asked MIT. I'm not sure the answer was. Is there just a ballpark answer? Is it 50%, 30%? For shipbuilding in general, maybe. Steel ship.
Okay. Okay. I can't.
Just real rough. Real rough.
Let me give you kind of a sort of an answer in a way that I can really cite realistic numbers that may give you some insight.
Jordan, repeat the question from the back.
Yes. The question was, what component of building a platform or a structure is related to labor cost as opposed to materials, et cetera? Okay? And it's not really fair to just talk about labor rates, because along with labor rates, you got to have some measure of productivity. Let me give you a non-answer that may still kind of satisfy where you're going with that. In my conversations with the good folks down in Galveston on this ship project that I'm involved with, they were talking about scaffolding. And scaffolding, I mean, how mundane is that? You're taking sections of pipe and whatnot, and you're making these joints, and you're just building a big ladder. Scaffolding. The cost of scaffolding is estimated in dollars per cubic meter. Okay? So however many cubic meters of scaffolding you need. Okay. In China, or Asian shipyards, scaffolding is estimated to cost $2 per square meter. And you have to kind of remember that the amount of labor to put scaffolding, it's basically labor intensive. Okay? $2 per cubic meter in Asia. In the Baltic states, $12 per cubic meter. Anybody want to hazard a guess in the Gulf Coast?
$30 a cubic meter.
$100 a cubic meter. Yowza. Now, that does not answer your question as to percentage, but it gives you a little bit of insight on there is real money to be saved depending on where you choose to have stuff built. And, yes, sir.
George, I have one observation and one serious question.
Okay.
Observation is when I see your floaters, there's a new very good industry for seasteading, prisons. And you send the prisoners to the Arctic, right? But more seriously,
yes.
Have you looked at the cost of maintaining the structures? Because when you say the cost of building is about 400 square feet, if you put one of those structures close to Honolulu, where I live, we are going to sell a lot of real estate. but the problem is how costly it is going to be to maintain them.
Yeah.
I can tell you that maintaining the house in Hawaii is much higher than, let's say, maintaining in Vermont. And once you put those structures on the water, it's going to be very, very costly. So did you look into the maintenance?
We certainly consider the cost of maintenance. I will tell you that at the level of detail in this parametric study, we have not gone to the level of trying to distinguish between different types of construction or different locations as requiring more or less maintenance. We've used kind of similar to my, so many dollars per cubic meter of scaffolding. Use parametric figures so that at the end of the day, your results are not skewed by using different assumptions in different platforms. I understand what you're saying, and that is very much a driver in our future focus on materials, because materials will have a great deal to do with maintenance cost. Steel is a very inexpensive material to build with. Steel is a very highly expensive, labor-intensive maintenance headache in the marine environment. Aluminum, not much better, really. Concrete seems to be pretty low maintenance. You need to have something other than steel rebar to really make it, I think, suitable for the long term. And that's where composites may ultimately shine, is in the reduced maintenance in the long term. And it's a complicated question. It's a matter of emphasis on potentially cheaper initial cost and long-term, high maintenance long-term versus, I would expect, higher initial capital expenditure, but longer life, not even just less maintenance, but longer service life. And we're not talking about the typical 20-year service life that is customarily assumed. If you're talking about a seastead community, you're talking 100-year service life or more, So, okay, I've got the high sign,
Yep.
and catch me at lunch.
Catch short of the break.
Okay.
Thanks, George.
Thank you very much.